Welcome to the CDT in Ultra Precision at the Institute for Manufacturing. Today I'm going to talk about the production of carbon nanotube-based field emission devices. But first, what is field emission? It is basically the extraction of electrons from a material. We do this by putting the device in a vacuum chamber where an electric field is applied. Distance from the emission point to the anode as well as the geometry of the device are important because it needs to concentrate electric fields to bend the work function of the material, allowing electrons to tunnel through it. Some applications include electron beamlines for particle accelerators, field emission guns used in high-resolution scanning electron microscopes, and also the generation of microwaves for non-lethal weapons. Now, there is a need for miniaturized systems. In the military, some approaches have been made using lasers like the Personal Halting and Simulation Response device. Civil applications also require the need to have portable X-ray devices instead of having big machines like the ones we see at airports. Just imagine the capability of having a small portable device that can be taken anywhere it's needed, and this project will enable these technologies. The targets of this project are to have high emission, reproducible devices, and a scalable production route using available industrial technologies. I'm using carbon nanotubes because they have high current carrying capacities. The nanotubes are made at the Department of Material Science, which are made by a chemical vapor deposition process. On one side, we inject a liquid source of carbon and iron catalyst into a furnace, and a black cloud condenses as seen in this image. This cloud is then spun out with a rotating spindle to form different variations of the material, such as films and fiber. Problems arise in great part by the material, as it has impurities, and up to today there is no way of controlling the chirality of the carbon nanotubes. So you'll always end up with a mixture of tubes with different properties. Another problem that we're encountering is the handling of these fibers and films. Because of their spinning process and storage, some of them end up having bends which will affect our field emission. To solve this problem, I've developed a new manufacturing route which stiffens the material, making it easy to handle, and then it is processed to manufacture a repeatable array which then undergoes quality control and field emission testing. The great thing about this process is that we have full control over geometry and dimensions, which allows customization for compact, reliable devices. Thank you for listening.